lecture series, we are now going to discuss the alcohols. We have already discussed, or we have already done 4 lectures on alcohols, in which we have done monohydric alcohols and dihydric alcohols. One of the main important reaction of dihydric alcohol is Pinacol-pinacolone rearrangement, which we are going to discuss today. Along with that, we will also discuss here trihydric alcohols. In today's lecture plan, we will discuss the Pinacol-pinacolone rearrangement. Then we will discuss trihydric alcohol, their introduction and nomenclature. We will discuss various methods of preparation of glycerol. We will discuss physical properties of glycerol like viscosity and solubility, etc. Then we will discuss the reactions shown by glycerol. We will discuss oxidation and dehydration reaction shown by glycerol. So, first of all, we will discuss the Pinacol-pinacolone rearrangement. Before discussing Pinacol-pinacolone rearrangement, we will first discuss the formation of Pinacol. Pinacol is tetramethyl-ethylene glycol and its IUPAC name is 2,3-dimethyl butane 2,3-diol. It is prepared by the reduction of acetone with magnesium amalgam. In Pinacol-pinacolone rearrangement, the 2,3-diol rearranges to butanone. Pinacol is converted to pinacolone. You can see here that this Pinacol has 2 hydroxy group at 2 and 3 position. When the Pinacol is treated with concentrated sulfuric acid, we get 3,3-dimethyl 2-butanone, which is also called pinacolone. We will now discuss the mechanism of Pinacol-pinacolone rearrangement. Mechanism of Pinacol-pinacolone rearrangement is completed in 4 steps. First step in the mechanism of Pinacol-pinacolone rearrangement is the protonation of the hydroxy group of Pinacol molecule. Formation of an oxonium ion takes place. In the second step, there is removal of water molecule and formation of a tertiary carbocation. In the third step of mechanism of this reaction, the methyl group present on adjacent carbon migrates with its pair of electron to electron deficient carbon. As a result, electron deficiency is generated at this place, and which is removed or which is stabilized by the transfer of electron from the oxygen. As a result, a resonance stabilized intermediate is generated. In the last step of this rearrangement, removal of proton results in the formation of pinacolone molecule. We will now discuss the rules which govern Pinacol-pinacolone rearrangement. In the present example, the stability of carbocation is the deciding factor for the mechanism of this reaction. You will see here that in this molecule we have 2 hydroxy group, one is attached to 2 methyl groups, whereas the other is attached to 2 phenyl group. If this hydroxy group gets protonated, the carbocation generated is stabilized by delocalization within 2 phenyl rings. Whereas, when protonation takes place at this carbon, the stabilization of tertiary carbocation takes place only because of the plus I effect of 2 methyl groups. As a result, this carbocation is more stable, and that is why protonation preferentially takes place at this hydroxy group, and there is formation of the product like this, and not this product is formed. In the present slide, we are going to discuss the Pinacol-pinacolone rearrangement of 2-methyl 3,3-diphenyl propane 2,3-diol. You can see here that, as we have discussed just now, the protonation will take place from this hydroxy group. As a result, water molecule will go off, and the methyl group present at the next carbon will migrate with its pair of electron. As a result, there is formation of a deficiency at this carbon. The removal of proton from this intermediate results in the formation of 3,3-diphenyl 2-butanone as the product. The second rule for the Pinacol-pinacolone rearrangement actually is decided on the basis of migratory aptitude of the groups. We have here either phenyl group which can migrate to next electron deficient carbon, then it can be methyl or a hydride. It has been found that the migratory aptitude follows this order, that is phenyl group preferentially migrates, then it is alkyl and then it is the hydride. In the present example, you will see that this 2,3-diphenyl butane 2,3-diol when undergoes Pinacol-pinacolone rearrangement, then either of the two hydroxy groups can be protonated because both the carbons are symmetrical or same. Now, when a hydroxide goes off after protonation, tertiary carbocation is generated. We have here phenyl group and methyl group. Out of the two, phenyl group migrates with its pair of electron preferentially. As a result, the product formed is 3,3-diphenyl 2-butanone. So, again we can repeat this thing that phenyl group migrates preferentially over the methyl group in this particular case. We will now discuss the nomenclature of trihydric alcohol with the help of certain examples. Like in this particular case, you can see that we have 4 carbon atoms. So, it is a butane, basically butane triol, but if we number the molecule from this carbon, then the 3 hydroxy group will take position 2, 3 and 4, but if we number it from here, then the position will be 1, 2, 3 triol. Okay, so that is why the rule which we have discussed earlier will be followed, that is minimum number is given to the substituents, and that is why the right name for this particular molecule is butane 1,2,3 triol. In this case, again the main chain is comprised of 4 carbon atoms, but if you number it from this carbon, the 3 hydroxy groups are present at position 1, 3 and 4. But if you number it from this carbon, this side of the molecule, the hydroxy group have 1, 2 and 4 position. So, the right name for the molecule is butane 1,2,4 triol and not butane 1,3,4 triol, because minimum number is assigned to the substitutions. Here in this example also, we have 3 hydroxy group present on 4 carbon chain, but at position 2 and 3 we have 2 methyl substitution. So, the name given to the molecule is 2,3-dimethyl butane 1,2,4 triol. In this particular example, one of the position is occupied by methyl group and the other by a cyclohexyl group. So, the name given to the molecule is 3-cyclohexyl 2-methyl butane 1,2,4 triol. We cannot number the molecule from this side, because then the 3 hydroxy group will get position 1, 3 and 4, which is not allowed. We will now discuss the methods of preparation of glycerol. Actually, in trihydric alcohols, glycerol, the first member is the most important member, and that is why we will discuss all the reactions and the preparations in this particular chapter, which will focus glycerol as an example. We will discuss now the methods of preparation of trihydric alcohols. Propane 1,2,3 triol is the first member of trihydric alcohol series, and we are going to discuss the preparation and properties which will be focused on glycerol only. Glycerol occurs in nature in almost all the fats and oils of vegetable origin or animal origin. They are present as glyceryl ester of long chain fatty acids like palmitic acid, like stearic acid, like oleic acid. It is obtained in large quantities as a byproducts from the soap industry and candle industry, and that is why we can also say that commercial source of glycerol is soap and candle industry. We will now discuss the preparation of glycerol from soap industry. First of all, see, this is the general structure for a fat or a oil, where you can see these molecules are large chain fatty acids. Actually, the fats and oils are the glycerol esters of long chain fatty acids. When they are treated with sodium hydroxide or potassium hydroxide, they undergo hydrolysis to form glycerol and sodium salt of fatty acids. Now, the sodium salt of fatty acids are called soaps. Along with the formation of soap, glycerol is also produced. This process is called saponification. When saponification is done on oils and fats, soap is formed in the form of sodium salt of long chain fatty acids, and glycerol is also formed. Now, when sodium chloride is added into this solution, soap precipitates out, leaving behind glycerol in the solution. This solution or this filtrate is allowed to settle for some time, so that the 3 to 5% glycerol is filtered out from this solution. After the separation of this dilute glycerol solution, the whole solution is distilled in vacuum in presence of charcoal. As a result, there is formation of about 90 to 95% glycerol takes place at this position. Now, from this 90 to 95% glycerol, pure glycerol of 1.26 specific gravity is obtained by distillation of this glycerol under reduced pressure. Glycerol can also be prepared by the fermentation of sugar. Sugars, upon fermentation with yeast in presence of sodium sulphite, give good amount of glycerol, which is then separated by filtration and followed by distillation in vacuum and under reduced pressure produces glycerol. We will now discuss some synthetic methods for the preparation of trihydric alcohol, the glycerol. Glycerol is prepared from propene or 3 carbon aldehyde or alcohol, which in turn are prepared by the cracking of petroleum. In this particular case, propene is first treated with chlorine to produce allyl chloride, which upon reaction with sodium carbonate followed by chlorine water and sodium hydroxide produces glycerol. In this method, propene is treated with chlorine at 500 degrees centigrade to produce allyl chloride, which upon treatment with chlorine water or hypohalous acid produces the dichloro derivative, which upon treatment with calcium oxide forms epichlorohydrin. Epichlorohydrin upon treatment with sodium hydroxide produces glycerol. These two methods which we have discussed here, you can see in all the cases, first of all, the propanol is converted into this alpha beta unsaturated alcohol or allyl alcohol by the treatment with lithium aluminum hydride followed by hydrogen peroxide treatment to produce glycerol. Propene upon treatment with water forms isopropanol. Isopropanol reacts with propanol to form acetone and allyl alcohol. Allyl alcohol then is treated with hydrogen peroxide to form glycerol. So, in all the methods so far we have discussed for the preparation of glycerol synthetically, it is either propene or propanol or propanol which is converted into propane 1,2,3 triol, that is glycerol. We will now discuss the physical properties of glycerol. As you can see that glycerol has one secondary hydroxy group and 2 primary hydroxy group, and that is why it can have hydrogen bonding with its own molecule as well as with water. As a result, it shows a number of properties, like it shows a very high boiling point to the range of about 290 degrees centigrade. It is soluble in water in all proportions, and it is viscous in nature, it is hygroscopic also in nature, and it is sweet in taste. So, all these properties of glycerol are due to the presence of 3 hydroxy groups. in the chemical properties of glycerol, we will see that most of the properties of glycerol are due to the primary or secondary hydroxy group. Now, it has 2 primary hydroxy group and 1 secondary hydroxy group, and since primary hydroxy groups are more reactive compared to secondary hydroxy group, this pattern will be seen in its properties also. Like for example, when glycerol is treated with sodium at low temperature, it forms monosodium salt with the primary hydroxy group, and when it is treated with sodium at a higher temperature, then the second hydroxy group also gets replaced by the sodium, or second hydrogen is also replaced by sodium, but it is only the primary hydroxy groups which react with sodium and not the secondary hydroxy group. When glycerol is treated with hydrogen chloride gas at around 110 degrees centigrade, then it forms monochloro-derivative. 2 monochloro-derivatives are formed. Here you can see the chlorine is replacing the primary hydroxy group, and here the chlorine is replacing the secondary hydroxy group. So, a mixture of these 2 monochloro products are formed, but when the same mixture is heated with hydrogen chloride gas above 110 degrees centigrade, then we get dichloro derivative. Here the 2 primary hydroxy group are replaced by the chlorine group, whereas here one primary and the other is secondary hydroxy group. So, it has been found that the products involving secondary hydroxy groups like this one and this one, they are formed in a smaller amount compared to products involving primary hydroxy groups. We will now discuss the reaction of glycerol when it is treated with small amount of hydroiodic acid. When glycerol is treated with hydroiodic acid in small amount, then triiodo derivative is formed. This triiodo derivative is very unstable. It removes one iodine molecule and forms allyl iodide. In excess of hydroiodic acid, on the contrary, there is formation of 2-iodopropane, which is the stable product. This product is unstable and is converted into propene after removal of iodine. When glycerol is treated with phosphorus trichloride or phosphorus pentachloride, it forms 1,2,3 trichloropropane. When it is treated with tribromide and pentabromide of phosphorus, the product is 1,2,3 tribromopropane. But when the same reaction is carried out with triiodophosphate, the product is finally 2-iodopropane. The reason is that first the triiodo derivative is formed, but it is quite unstable and forms the allyl iodide. Now, since in situ phosphorus triiodide reacts with water to form hydroiodic acid, and this hydroiodic acid converts allyl iodide into 2-iodopropane, as we have discussed in the earlier slide. With nitric acid in presence of concentrated sulfuric acid, glycerol is converted into trinitroglycerine, and this trinitroglycerine, when absorbed over a type of clay called this kieselguhr, the combination is called dynamite. Here we are discussing the esterification reaction shown by glycerol. It has been found that glycerol, when treated with acetyl chloride or with acetic anhydride in presence of hydrogen chloride gas, it converts, or all the 3 hydroxy groups gets esterified. It forms glyceryl monoacetate, glyceryl diacetate and glyceryl triacetate. Glycerol reacts with excess of oxalic acid at 110 degrees centigrade to form glycerol as well as formic acid. First of all, there is formation of glyceryl monooxalate, which removes a molecule of carbon dioxide to form glyceryl monoformate, which upon removal of water molecule forms formic acid and glycerol. If glycerol is treated with excess of oxalic acid, at higher temperature, then a cyclic intermediate or cyclic compound glyceryl dioxalate is formed, which upon heating removes two molecules of carbon dioxide and generates allyl alcohol. Glycerol undergoes dehydration when treated with potassium hydrogen sulfate and forms acrolein. Now, we will discuss the oxidation of glycerol. It has been found that when glycerol is treated with different oxidizing agents, it produces different products, like for example, upon oxidation it forms glyceraldehyde, it forms glyceric acid, tartanic acid, dihydroxyacetone, mesoxalic acid and oxalic acid. You can see here in this slide that glycerol when treated with dilute nitric acid produces glyceric acid, when it is treated with concentrated nitric acid produces glyceric acid and tartanic acid. Upon treatment with hydrogen peroxide in presence of ferrous ions, it forms glyceraldehyde and dihydroxymethylacetone, whereas with bismuth dinitrate it forms mesoxalic acid, and with a very strong oxidizing agent KMnO4 it forms oxalic acid and carbon dioxide. Degradation of the molecule takes place over here. Glycerol reacts with aldehydes and ketones and produces cyclic acetals and cyclic ketals. Two series of cyclic acetals are possible because we have here a small substitution of hydrogen in case of aldehyde, whereas with ketones only one set of ketal is formed. Glycerol find a number of uses in various industrial produces, and these uses have been summarized in this slide. You can see here that this glycerol is the basic ingredient of gums and resins. It reacts with nitric acid and sulfuric acid and form the explosive nitroglycerine. It is used as a softening agent and stabilizer in ice creams, and it is also used for freezing red blood cells, sperm cells, eye cornea and other living tissues. Then earlier it was used in as automotive antifreeze, but nowadays this use of glycerol has been replaced by ethylene glycol. We will now summarize what we have so far done in this lecture. First of all, we did the Pinacol-pinacolone rearrangement, we did its mechanism and certain rules which are followed during the rearrangement procedure. We have then discussed the preparation of trihydric alcohols, we have done the nomenclature of trihydric alcohols also, and after that various reactions shown by glycerol as well as its uses. So, with this we have finished the lectures on alcohol series. In the next lecture we will discuss something about phenols. Thank you very much.